So let us prove this embedding. Indeed, we use this trick method today before. So what should we do? We will fix any function from LQ and try to show it can be decomposed in sum of two functions. There is very natural decomposition. We can take set A as x such that function is smaller than 1, larger than 1, and set B x such that the value of the function less or equal than 1. Of course, it will give decomposition of the set E, and then we will have that f is sum of f characteristic function of A plus f characteristic function of set B, of course, since decomposition, and clearly that f characteristic function of set A belongs to LP. Why? If this is integrable, if the function is integrable, integral of q degree is integrable, but p degree is smaller, yeah? P degree is smaller since f larger than 1. So we have that one, and function characteristic, this product belongs to LR. Okay? It's clear. More useful, the next and the last proposition in this line, that if a kind of interpolation, it's a kind of interpolation result, we have that for p again from 0, smaller than q, smaller than r, less than infinity, no restriction on measure of set E, finite or infinite, always, we have that LQ is inside or LP intersected to LR. In many situations, this is useful. So we have LP. In general, it's not the same as LR. There are no embeddings, as we'll see with you. But for all intermediate Q, for all Q between them, for all intermediate Q, we have LQ inside of this intersection. Okay? Indeed. We will. Wait a minute. Let's do this. Wait a minute. I'm not sure. It seems to me it will be the same for. Let's put 1 here. You can analyze the case if this is p smaller than 1. It seems to me also we will have this, but you can analyze it yourself. But if in this situation we can use Hilbert inequality, since now norms are well defined, etc., etc. And we can use Gölder inequality for in the following way. Okay, I will write immediately the result, and then you can check it yourself. Indeed, we have that Q norm is less or equal than P norm in degree kappa, and here R norm in degree 1 minus kappa, with some parameter kappa between 0 and 1, of course. And this parameter can be found from the following inequality, for following condition. We have 1 over Q, it is kappa over P, plus 1 minus kappa over R. Okay? So this is the proof. If they are, we will have this condition. If this is finite and this is finite, that is function belongs to intersection, then this is finite, that is function belong to the class LQ. And how to prove this? In principle, using the same method, but only the problem that now we want to show that this integral is finite, yeah? Integral is finite. Now the method is to decompose, to write this as a product of two functions. So this is integral f alpha and here f beta. And then to use Gölder inequality. Gölder inequality with corresponding parameters. So this is the idea of the proof. You can follow this method yourself easily. If you want, we can write this. We can find corresponding alpha and beta. Indeed, alpha and beta, they are given by this condition. Okay, etc. So we have this proposition, interpolating result. Corollary. Important class of integrable functions, the spaces of integrable functions are spaces of sequences. Spaces of sequences. Space of sequences, of course, this is, we understand with you that LP, which are sequences xn from 1 to infinity, such that xn is finite, xp degree is finite. Of course, it is space of integrable function, LP, over the set of natural with counting measure. With counting measure. And norm is given if p is larger than 1, more or equal than 1 in natural way. And now for this space of sequences, we look for set with finite measure. We have embedding that space with large index is inside of small set with index which is smaller, yeah? But now we will have inverse. Now we have in general, for any set with infinite measure, as we will see now with you in 5 minutes, we do not have embedding at all of any kind. But for this special set with infinite measure, we have, that is, if p from 0 smaller than q, less or equal than infinity, then we will have that LP inside of LQ. Inside of LQ. Okay? And what is more, if p is larger than 1, more or equal than 1, then also we have then this p norm of any element is less or equal than corresponding q norm. Corresponding q norm. Use the proposition 3 with r equals infinity, and then we will have this condition. Okay? Okay. Now questions. No, wait a minute. We have to take q is larger than p. Q is larger than p. Now we will have that one. So it can be done from here or can be done directly, but not by if you take r equals infinity. We can check it directly. Or we can get it from proposition 3, but with some another choice of parameters. LP inside of LR. Okay, I don't want to do this now. The next question is what we will have in general if mu e is infinity. That is, if for some special case, we have embedding of that type, but in general not. Then we have that LP mu or mu e or e mu is not inside and does not contain LQ e mu for any p, for very different p and q. And what is more, see, always it's possible to find just one function, and I want to give this function now, which will belong to this class, but will not belong to any other class, for any other q, smaller or larger than q. You understand what I want to say? It's not the same that for any q larger than p, there exists the function g such that does not belong, g belongs to LP but does not belong to LQ, and for any r smaller than p, there exists some function h such that it's the same, but it's we can show only, just one function which will provide all value q and r, nevertheless are they smaller or larger than p. For example, for the case in LP R plus with Lebesgue measure, we can take the function. I'd like to recall you simple stuff. Simple stuff from calculus is the following: that if we consider the function 1 over xp, then the case when p is larger than 1 is good for infinity. Here we have convergence if p is larger than 1. And here we have convergence if p is smaller than 1. The good case near the 0 if p is smaller than 1. Therefore, in principle, there is no function of the type xp, which will, there is no p such that 1 over xp belongs to L1 on the line. on the half of line, yes? But we can take the function just with simple modification of this. We can take function fx, which is x and logarithm squared x plus 1. Let's take this one. Yeah. And now 1 over, minus 1 over p. Okay. Let's take this function. Yes, let's take this function. Of course, on this r plus. Then what do we have? We have that integral. Of course, it will be usual Riemann integral, since function is positive. From 0 to infinity, dx, and here, I mean p degree. We have this Lebesgue integral of p dm on r plus. It is the same as the Riemann integral from 0 to infinity, dx, and here x, and here logarithm squared x plus 1. But this is very good integral. It is arctangent, yeah? It is arctangent of logarithm of x from 0 to infinity. It is minus infinity here, plus infinity here, but it's not the problem. Then integral, not only integral exists, but we can show explicitly the value of this integral, okay? This is clear, yeah? Now, but now we have the following. For any q smaller than p, we have now integral, this fq will be infinity. Integral diverges. This integral diverges. Why? Since if q is larger than p, we will have integral of the type. Of course, this logarithm, we understand with you, it's not important near the no infinity, nor near the 0, since this logarithm has behavior much, this logarithm is much smaller than degree of x, any degree of x. Since, therefore, if you take q smaller than p, and if you try to calculate this fq, it will be something as the integral dx, and here x at degree 1 plus epsilon. 1 plus epsilon. We will have problem near the 0. We'll have problem near the 0. Since this integral near the 0, and here dx, and here x, q over p, and some logarithm, it's not important now, q over p is infinity. And on the other hand, if q is larger than p, then we will have, wait a minute, q smaller than p. Q smaller than p, we will have the problem near the infinity. If q is smaller than p, smaller than infinity, if q is larger than p, then the corresponding integral near the 0. If q is infinity by the same arguments. I hope you understand this stuff, yeah, from calculus. Of course, you can say that this is the smaller than 1, but here there is some big term in denominator. But this term, of course, is much smaller. We have that x at q over p, and here logarithm squared x plus 1 in degree q over p. Of course, it will be larger than 1 over x of 1 minus epsilon for some epsilon. For some epsilon. So this integral diverges, so this diverges, it's clear, yeah? But near the 0, easy to see. Now, and in principle, the same can be done not only for this case, but for other measures. Borel, for other Borel measures, we can do the same stuff. We can take some part which with infinite measure and take here some characteristic function or sequence of functions of that type with corresponding stuff with convergent at infinity only degree p or more or little than p. And also here decompose in some parts and here take some functions of that type. Since that now we will have divergence for q smaller than p. So repetition of this, some discrete repetition of this discrete variation of this function. Okay? So let us return to these pictures. Yeah. Here we have situation for any set with any measure. For any measure, for any set. Now, if set has finite measure mu e, then we will have the collection of the increasing collection of functions. This is the smallest one, L infinity. This is the largest one, L0. So, and this LP. Okay. Now, if we have very special case, if mu e is finite, then we have this. Now, if we will have rather special space that is n with counting measure, then we will have LP spaces, L small p spaces. Then we will have inverse. Then
about proposition 3, don't we have a problem?
Huh?
We have a problem, I think, in
Really?
proposition 3, yes.
Let's check it. Okay, let's prove it if you want. We have for this some time. P is larger than 1, smaller than q is infinity. Then what is the statement? We have that LQ is inside of LP and here LR. And what is more, I wrote here that the norm Q less or equal, norm P here kappa, norm F R 1 minus kappa. Okay?
For example, in this picture,
In this one.
yes,
Uh-huh.
how can we say that?
Easily, because we take this is intersection.
Yes.
This is intersection, you see? Therefore, if we have that function from LP, so this is LP, then it is LQ is inside of LP.
Yes, but not inside.
It's not mean, it doesn't mean. So what does it mean? It means the following: if you take function f, then belongs to LP, and f belongs to LR, then it means that f belongs to LQ. We have this condition. So in principle, in this situation, we have to take, for this picture, we have to take function only from here. If you want to have something inside of the this intersection, okay? For that case. Wait a minute.
Inclusion is...
Okay, let's try to prove this, and then we will see. So we have that if this is finite, this is finite, this is finite, so LQ is inside. LQ is inside. Okay. So once more, what is the problem? What is the problem? If you take function from here, yes? So this belongs to LQ. Where is LQ? This is LP, and this is LQ for this situation, yes?
Okay.
So what's the problem? We can't take function from here, since it does not belong to LP, LR.
Inclusion is...
Of that type.
Yeah, no, it must be LQ includes.
LQ includes. Once more, if this is finite, this is, yeah, you are right, yeah, of course, this one. So if this is finite, this is finite, this is finite, yeah, I'm sorry. We have this in general, yeah, so picture is not good. We have that LQ contains this intersection. Let's by the way prove this proposition. Okay? Yeah, sure. And of course from here, the corollary that I say you before, now we understand that LQ is inside of LP if Q for P less or equal than Q, and here indeed we can take R equals infinity. So yeah, I was wrong. So of course we have wrote. Now if we take this infinity, then we will have L small p is inside of L capital for Q larger. No. Okay, let's see this now. Now inverse. LP is inside of LQ. Any summable sequence is bounded. For example, if Q is equal infinity, then we will have this immediately. Okay, I suggest let's prove this, okay? Of proposition 3. So, once more, what is the idea? Idea is to check that FQ, now we have function belongs to this class. We want to prove that belongs to this class, that the problem indeed to show that this is finite. Is it true or not? Now, what we will do? We will write this FQ as integral F alpha and here F beta, and then we will apply Hölder inequality. In such way that we want to have here P degree, and here we want to have R degree. Suppose that R is finite. So we will want to have this stuff. If we will have, so we apply Hölder inequality with some conjugate parameters, 1 over P1 and 1 over Q1. Okay, the sum is 1. Yeah, we will apply Hilder inequality. So it means that this P, it is this alpha, or maybe is immediately it's better to write here alpha Q and here 1 minus alpha Q. Let's write it that way. So now alpha will be definitely something between 0 and 1. We can do this. Now, what is P? P, it is alpha Q multiplied by P1. Since we apply Hilder inequality, that one. And R, it is 1 minus alpha Q multiplied by R, by Q1. By Q1. Okay? So we have now a kind of system of equations. And here, since it is Hilder inequality, it will be 1 over P1, and now it will be 1 over Q1. 1 over Q1. So this is Hilder inequality. Now, what do we have? We have a system of equations. Indeed, there are three conditions. This is first condition, this is second condition, and this is third condition. Yes? Third condition. With three unknowns, P1, Q1, and alpha. So let's find it now. For example, we can find 1 over P1 from here. 1 over P1, it is alpha Q divided by P, and 1 over Q1, it is, check me please, I am not in good form today. 1 over P1 is alpha Q divided by P. Yes, it is 1 minus alpha Q divided by R. Yes, 1 over Q1. And then since the sum is 1, we have alpha, and here Q over P plus 1 minus alpha, and here Q over R equals 1. So alpha, it is just the kappa that I gave you, yeah? Before. So alpha, it is just the kappa. So maybe it is better immediately to replace here, to take, instead of alpha, to take this kappa, yeah? So, from all this writing, we see that in principle, it's possible to find alpha satisfying this condition. Therefore, what do we have? We have that 1 minus alpha Q divided by R equals 1 minus Q over P. Yeah? Something wrong again, because it should be inverse. It must be, okay, let's check it again. 1 over P1. 1 over P1, alpha Q divided by P. P, it is alpha Q multiplied by P1. Now, here minus alpha Q multiplied by Q1, it is R. 1 over P1, it is this stuff. 1 over Q1, this stuff. Something wrong, it should be positive, yeah? We have Q over P. Okay. Wait a minute. Alpha. This is alpha here. I forgot about this alpha. I'm sorry. So, now, I'm going to find alpha. What is alpha? Alpha Q over P minus Q over R. Definitely this is positive. Yes? It is 1 minus what? Q over R. Yeah? Now, therefore, we can write it just in this way. So this is 1 minus Q over R, and here Q over P minus Q over R. If you want, you can simplify it. Yeah? So it is R minus Q. I'm not sure it's a good simplification. Let's fix it this form. Clearly, then this is something from 0 to 1. It's easy to see that it's positive. It's not difficult to check that this is 1. Therefore, there exists this alpha. If there exists this alpha, we will write all this chain, and now from here we will have, if I will take, I want to replace now, I want to take, instead of, if you do not object, I will write just here, instead of 1 over P1, immediately alpha Q divided by P, and here immediately this 1 minus alpha Q divided by R. And then we will have from here, if we take degree 1 over Q from both parts, we have that Q degree less or equal, that Q norm less or equal than P norm, and here we will have this, it is just P norm, yeah, alpha, and here R norm, in degree 1 minus alpha, just what we are looking for, only alpha instead of kappa, yeah? Now, of course, you are right in the sense that this embedding should be inverse, since now, if this norm is finite, then this norm is finite, yeah? That is, we have this embedding. And now, if we take r equals infinity, then we will have that, definitely we have that LP, okay, we understand that any LP is bounded, therefore we will have that this LP, if you take any from LP, it will be inside of LQ. Okay, thank you for correction, but I want to repeat to these pictures again. For finite measure, we have this increasing situation if mu e is finite. For special set, for special measure space n with counting measure, we have inverse situation. This is L infinity. Now we have inverse situation. This is L infinity. It contains all of them. But in general, if mu is infinity, we have nothing, yeah? So, of course, there are functions which belongs to all classes, but there is a function in LP that doesn't belong to all others, yeah? So this is the function from LP, such that we take all other spaces, but they do not contain this function. Of course, it's not a problem, but this is the life, so keep in mind this example.
Proposition 3 is valid in general.
Yes, absolutely in general, in the sense that for any measure, for any measure and for any space, for any set, finite or infinite measure. And what is more, it seems to me that we can write here P is positive. That is to consider this. Of course, now this proof does not work. Since we have Minkowski, we have this Hölder inequality for conjugate exponents with P larger than 1. We can apply Hölder inequality, yeah? But it's interesting to see that is it true or not if P is larger than 1, if P is larger than 0. It's interesting to check. It seems to me that it's valid also. I don't want to do this now. But at least for this situation, I mean that always for any measure, okay? This interpolating kind of result. Okay, now let's continue. So please your questions about this one. About the, so we have this is about embedding of spaces. Now about topological embedding. The spaces, they are very different. The spaces, I mean LP for different P, or maybe real positive, or the spaces LP are very different. Very different, I mean not between the cells, but in the same collection, indeed they are very different for the same measure space. Even if you have embedding, for example, mu is finite, then as we discussed with you, we have that L infinity is inside of etc., etc., and here we have LQ inside of LP, yeah? That even, or maybe, again, L1 is inside of LQ, etc., etc., L infinity, yeah? That we have these embeddings only a set of elements. Of course, they have different topologies, they have different norms. And what is more, these are not only, of course, they are linear subspaces, but they are very small in the sense of category, for example. We have here that LP, for example, is of the first category in any LQ for P smaller than Q, okay? So this is small, very small, even in the sense of category. Of course, it's not rare, yeah, because definitely the closure, we understand with you that the closure of any LP, but closure with respect to Q norm, of course it will be just give LQ, yeah, the completion. The corresponding completion will give LQ norm. But nevertheless, it is countable union of Nova-dense sets. In the same situation here, that we have that LQ, I mean for this situation, LQ is of the first category in LP. LP also, Q is smaller than Q. Also here, P is smaller than Q. Okay, here more difficult to represent, but it's possible also to show that the sets are first category. So topologically they are rather different, and there are some results about the operators between the spaces, their singulars, etc., etc. Now, this is more from functional analysis, not from our course. And there is one more, the last result in this line, without proof, since again this is from functional analysis, closed graph theorem. And this last result is the following, that closed subspace consisting of bounded functions must be finitely dimensional. It is a theorem without number. So suppose that Y, it is closed subspace, linear of course, subspace in LP, in any space LP, with finite measure. LP, E, we suppose that measure E is finite. And we have that Y consists of L infinity functions. It's kind of this discussion, yeah, but much stronger now, because not only of the first category, this linear subspace is finitely dimensional. So this is the theorem. We have the dimension is must be fine. Of course, for finite dimensional, no problem. We can take any collection from here, take span, and then we will linear span, and we will have closed subspace, closed linear subspace. But in principle, for any, I mean the inverse result. If you take any subspace, closed, consisting of, that is any dimension, any subspace of L infinity, yeah, and we take the closure of this subspace, then it must be the whole LP, the whole LP. It's impossible to have infinitely dimensional subspace here, okay? Closed subspace. Proof by so-called closed graph theorem. Closed graph theorem can be done. Okay. So I think that it also maybe can be extended to this space, not L infinity, but maybe some LQ larger than P, I'm not sure. So this is another illustration that spaces are rather different. Spaces are rather different, topologically. Even in the case if measure is finite, we have embeddings, but as a sets. Now place your questions about this stuff. It was 8.3 about embeddings, relations between the spaces. The next one that I hope to finish today, in order to, and maybe Hilbert spaces, I will recall you some facts from functional analysis. In order to in mind, you will consider the situation with dual spaces to integrable functions and finish our course. The last lecture is on Tuesday. If you want, we can arrange a consultation. Okay? I'm ready to give you a review of the whole course. And if you will ask me questions about some concrete subjects, we can repeat. So now 8.4. 8.4, another interesting question. If space is separable, it means that we can choose some countable system and approximate any element by elements of this countable system. And how to choose this countable system? Indeed, we consider this with you today, yeah? We can approximate by these functions. We cut the function f, but there are some other useful methods. So let's look at this subject. Approximation. In LP. Let's consider P Banach space. Let's consider Banach space, and let's consider the case when P is finite, since otherwise, but measure not. Maybe set with infinite measure, but P is finite, since otherwise space is not separable. It's not very interesting to approximate functions in non-separable spaces. Now, so we understand that this space LP, E mu, is separable for any E and for any mu, yeah? For any mu. Okay. Now, there are different ways. So, we can approximate then any function f from LP can be approximated, yeah? By what? So let's look, what can we do? By simple functions. Of course we can do it, simple functions. Simple functions, the collection of simple functions of course is not countable, but nevertheless there is some way of approximate, and we will use it in the proof of many problems. Now, by continuous functions, this is Lusin, yeah? Continuous functions, Lusin theorem. Since we can any measurable function approximate for integrable, yeah? In principle, of course, we discuss here approximation in the sense of the norm. In the sense of the norm. By Lusin theorem, we can approximate pointwisely on up to the set of a small measure. But if function is integrable, it means that indeed we can, for fixed function, we can use not only Lusin but even Egorov theorem. Yeah, since given epsilon, we can remove these tails. And then to consider set on finite measure up to epsilon. Yeah, and then here we can approximate in any good way by almost uniformly, etc., if we have almost everywhere convergence. Now, and the same for Lusin. So we can take function here 0 and here 0, and here we can approximate this function, given function f, by continuous function only non-compact interval. But if we can do this on compact interval, then this continuous function that will be rather close to function f by Lusin, we can approximate the polynomials, yeah? But now, by polynomials locally, we can do this. Yeah. So I will write this explicitly. By polynomials, but now the supposition if mu is infinite, since again not good. Yeah, maybe it's better to write that E is bounded. E is bounded. Yeah. Then we will take some compact set containing E and we'll start to do this. Since in general, even if mu is finite, then we cannot do this, since function may be small, but polynomials, they have a growth at infinity in principle, you see? So at least in this situation.
This subset of line, yes?
Huh?
Is the subset of...
In general, not. In general, not. But here, yes. Since Lusin theorem we proved with you.
How can be polynomial in general?
Then we suppose that there is a linear structure on the Z. Okay, let's consider this on the yes, let's consider on the line. Okay, since I don't want to in Euclidean space. Okay, you're right. It's better to write this in Euclidean space. Now, the next method after polynomials, which is rather useful, we can approximate by functions g which are from C infinity 0 on this Rd. So this is infinitely differentiable functions. This is infinitely differentiable functions with compact support. By definition. This is good space. It has its own topology. Not metrizable, not normable. And again, it's more or less clearly for us here, because if we have a function in Euclidean space, then we will take some big ball, yeah, neglect the space outside of this ball. And since in this ball we can approximate by continuous function, of course this continuous function can be approximated by infinitely differential. This moves clearly. Now, this method is rather useful. This method is by convolutions. It seems to me that we considered with, at least I gave some definition of the convolutions in some previous lecture. And what is more, the problem number 3 in the last homework about stick law functions. Stick law functions, they are just particular case of convolution, yeah? By convolution. So what is the convolution? Convolution is the following. We take function rho, fix. We will fix function rho, which is integrable. Integrable in any Euclidean space, but in sense of L1. In sense of L1 integrable. And we will take function rho epsilon x. Rho epsilon x, it is epsilon minus n, and here rho of x divided by epsilon. Okay? Now, if function is integrable, we understand, so it will be just kernels for approximation, yeah? Look, if function is integrable, clearly that if we will move epsilon to 0, yeah, then for given function rho, we will have something like this, epsilon smaller, smaller, and smaller, okay? Now look, for example, this is normalizing term, normalizing coefficient. If we take, what is Steklov function? Steklov functions are defined maybe in this way, is 1 over h as I gave you, or 1 over 2h, let's take 2h, and here we have x minus h, and here x plus h, and here we have f of t dt, yeah? So, what is this? This is convolution. This is convolution. Now, we can take, then we have that convolution of function f with this rho epsilon approximates function f in the sense of the norm p, in the sense of this p norm. You remember the definition of convolution, yeah? So f g x, it is the function which is integral for this space, for this Euclidean space, and here f of x minus y, g of y dy, okay? Now, in this situation, we take the function which is minus 1 here, 1 over 2 here, yeah? So this is function rho. If you take this function rho, which is integrable on the line, and the integral is 1, I did not write this unfortunately, so write this rho dx for the whole space must be 1, okay? Since otherwise what's the reason to introduce this coefficient? Please write this condition. Now, this integral is 1, this integral is 1. This is convolution. This is convolution. And this convolution has nice properties, yeah? We approximate it in the sense of the norm, also pointwise, these functions, for example, approximates in measure, etc., etc. Very good way to approximate the functions. The last one that I want to recall you, that we also discussed with you before, that there is also a basis by basis elements, okay? Means so there is topological basis. There is a topological basis. Of course, no chance to find topological basis in non-separable space. What does it mean, topological basis? Topological basis means the following: if X is topological vector space, then we will have that some system En, it is from 1 to infinity, topological basis. If you have the following: for any element of this space, there exists unique set of coefficients psi n such that the series psi n En converges just to X in topology of this space. In topology, this is topological basis. And in good situation, this is so-called Schauder basis, that the corresponding functionals are coefficients, are continuous. And it's possible to show that if there are many bases in this spaces LP, again, if P is larger than 1 and smaller or equal than 1 is strictly finite, then the Haar system is a basis, topological, is the topological basis in LP. Okay, let's take minus 1, 1. Since this defined on minus 1, 1. Or in any interval. I gave you somehow this definition of Haar system. When we considered with you convergence in measure, it was there is sequence which convergent in measure, but divergent everywhere. You see there? I say that it's interesting not only because of this example, but since important Haar system, it is also has the same behavior. We take interval on the interval, minus 1, 1, for example. We take the first function, which is 1. Then the second function, we take up to normalization here, minus coefficient here, plus coefficient, and this is E1, E2, etc., etc. Then we typical hard function. After this binary decomposition, we have function which is some coefficient here, another coefficient here. In such way, it's usually better to play with orthonormal basis, such that the corresponding norm of the function is 1. So this is useful, very useful method to approximate the functions, and here they are just approximation in terms of the same elements. Advantage of topological basis. Okay. Since you were late in this hour, I will give the lecture another 5 minutes. Okay, no, it's a joke. I will finish now. Indeed, not only hard bases. There are a lot of other bases. For example, now, the last 20, 30 years, wavelets is a kind of fashion. Many people found that wavelets. It was clear that wavelets, they combine advantages of different orthogonal systems, some another systems. For example, this is the simplest, we can say this is simplest wavelet system. And there are different wavelet systems and spaces of integrable functions, not only of them. On Monday, we will consider with you a special case. The special case L2 on any set E with respect to any measure mu. It is Hilbert space. Hilbert spaces are the best in analysis after finite dimensional. And of course, if you talk about the basis, any Hilbert space has at least Hilbert basis. By the way, this topological basis exists not always. Vector basis exists always by axiom of choice. But topological basis exists not always. For example, in non-separable space, definitely there is no topological basis. Another result, which is rather non-trivial. If you take LP for this P is smaller than 1, then we will have the dual space is extremely poor here. It contains space of linear continuous functionals, contains only trivial functional. But there is the result that if you have metric space, and if metric is translation invariant, clearly what does it mean, and with basis, then it's possible to show that the corresponding functionals which are given in the way that for any x we will take the corresponding value psi n of x. So this is psi n of x are continuous. It's a kind of Banach theorem. Banach proved that continuity of Banach-Schauder theorem that the corresponding functionals are continuous for Banach space or for Fréchet space. And here in principle for any complete metric space with basis but translation invariant metric. And here it is complete metric space with metric which is translation invariant. That is, we have D, Fg, it is the same as D, F plus H, G plus H, yes? So trivial, it's translation invariant. But it's extremely poor dual space. Therefore, we have that LP has no basis, has no topological basis, non-trivial result. But for example, this P has a basis. We have a small p has a basis, We can take usual orths from 1 to infinity. So this is from basis theory. We see that topological basis exists not always. This is the life, unfortunately. But for good situations, it exists in this very good way to approximate the elements. Okay, so I suggest the following plan. We have 3 lectures. On Monday, we will finish the course. I recall you without proof some facts about Hilbert spaces, indeed from course of functional analysis. And also, I've read it again without proof, the theorems about dual spaces. It will take at least 1 hour to prove them about dual spaces. And that's all. And on Tuesday, you are welcome for the last farewell lecture, consultation, review of the course. Okay, that's all. Good luck.